Welcome to chapter 2. So, in chapter 2, we're going to focus on logic. So, we're going to start with talking about what is a logical form, what's logical equivalences, and what are some of the different logical notations that we have out there. So, first, we're going to address logic, and that's pretty much we're just going to do all this section. So, what is logic again? It's a formal language of representing knowledge or making logical inference. So, it's a whole field in and of itself, and people spend lots of time studying it. It also helps us understand how to create a valid argument. The truth is, most people are really bad at logic. They create arguments that are based more on emotion than they are on logic. And are they true and false? We have to understand the syntax and the meaning of different statements. So, and the rules or manipulation of logical inference. So, this is where we're going to attack, is we're going to get into some of the syntax and what things mean, and we're going to practice this a little bit. So, we're going to start with what's called propositional logic. It's the easiest or simplest. A proposition, also called a statement, is something that's either true or false. For example, if I say the UC is located on the campus, that's either true or it's false. We can't like say, well, maybe it's true. It depends on this. It is black or white, true or false. If I say 5 plus 2 equals 8, that is also false because we know 5 plus 2 is 7. It's not 8. We can move on. If I say it's snowing today, well, I would say it's either true or false because it depends on what day you're watching this. So it could be. So this is still a proposition because it's going to have a true or false because it depends on what day you're watching it. But as soon as you have that day, it's definitive. So we would call this still a proposition because the only difference is you are probably not going to watch this necessarily on the same day I do. So let's look at some more examples. How are you? This is a question, so it's not a proposition. X plus 5 equals 3. This is the same thing. X is not specified, so it's neither true or false. So just like the today one, it actually gets into a fuzzy area. If, however, because I defined today, and that's definitive, so whenever you watch this video, today is, well, that day. But this one, X could be anything in the world. And depending on what we pick, this is either true or it is false. So because X is a variable we don't know, 2 is a prime number. Well, this is an easy test, and it is true. Talking about prime more. She is very talented. The problem here is we used a general term in she. Because of that, we have no way of knowing who she is, and it makes it kind of hard to say if this is true or false. So we have to be careful about statements and recognizing. So your first part is identifying is something true or false. After that, we start using what are called composite statements. This is where we connect two statements using some kind of logical connective. This is where our notation is going to start coming to play. So for instance, I have two propositions here, and you can quickly see them in terms of it snows outside and we will play chess. It's true or false, each one. If it snows outside, then we will play chess. Notice how I connected them with an if-then statement, and this is where we get into the whole we can move on and kind of imply things. Well, our logical connectives are going to be this grouping right here. We're going to talk about negation, conjunction, disjunction, exclusive or, implication, and biconditional. The latter two, implication and biconditional, or conditional and biconditional, will actually be in section 2.2. We are not going to get into those during this video. We're going to get into the first four. Exclusive or is not really even one we're going to spend a lot of time on, but it does exist out there and I want to mention it. So what is negation? So negation, again, so we're going to start with P representing some proposition. So we take anything, we kind of melt it down to, again, a variable. Usually P and Q are the very common ones. And so we say negation is meaning something is not true. And we are going to use this little symbol here, which is kind of a line with a straight down bracket. That is the standard symbol for negation that we're going to use over and over. Occasionally you see something that might have like a tilde symbol instead here. Be careful for all of you that have learned maybe Python, you might want to use an exclamation mark. We are not going to do that. this is the symbol that we use in mathematical logic. So be aware of that. So suppose that I said the BAS is located on the TME2 campus. The negation of this is it is not located on the campus. If I say that 5 plus 2 is not equal to 8, the negation of that is, that's how we negate it, is we do a slash through. 10 is not a prime number. It is not the case that buses stop running at 8 p.m. Adding not, but we got to figure out where's the appropriate spot and other things like this. So what does that look like in different things? So I want you to pause the video. How would you negate this statement? It is snowing today. All right. Hopefully you did that. It's not snowing today. It's an easy one. Let's do this quickly. How would you negate this one? 2 is a prime number. 2 is not a prime number. Okay, that's easy. There are other forms of life on other planets in the universe. It is not the case that there are forms of life on other planets in the universe. You could also say there are no other life forms on other planets in the universe. There's a lot of other ways to have negated this. And that's where it gets fuzzy, is sometimes these things can be written using English a lot of different ways. This gets us into something known as truth tables. So truth tables are a very nice way to visualize the relationship between true and false values. So for instance, here I wrote down P and it has two possible values, it's true or false. The not P, if P is true, notice, if P is true, then not P is false. And if P is false, not P is true. That's all it is, just flips the opposite. So again, we get used to doing these truth tables where we put what we have up here and put all the options, and then we list the next ones and so forth and so on. Now let's talk about conjunction. So a conjunction is where we get the word essentially and. So we now have two propositions, P and Q. The proposition P and Q, notice we denote this with this almost like upside down V or a wedge. Mountain, whatever term you want to use, that's what we use for it. The proposition is called the conjunction. So this is a new statement. So for instance, if I said the BAS is located on the campus and 5 plus 2 equals 8. Well, that is the conjunction of those two statements. What if I say it is snowing today and 10 is not a prime number? So now I did a conjunction and a negation. Notice the negation is applying to just the second portion, not to the whole thing. So and 13 is a perfect number. You don't know what perfect numbers are, but I'm just trying to give an example. And 4 is a prime number. These are examples about how we can attack these things and kind of work our way through them. Now, when we're dealing with these conjunctions, it's important for us, it's important for us to understand when these are true and false. And I'll come back to these in a second. Let's go to the next one, which is a disjunction. Namely, a disjunction is going to be the or symbol. And notice all it changes, I take the same symbol and I flip it upside down. So you have to be very careful about knowing which one is an and, which one is or. Or is a V shape, and it's called a disjunction. And notice, I'm going to come back here. The conjunction is true when both are true and false otherwise, which means if either one of these statements is false, then we have a problem. So the BAS, it is on campus. However, we also know that 5 plus 2 is not 8. So this statement right here is actually false. So let me write that in real quick. I can write that that is false. It is snowing today. So right now, where I'm recording this, it is snowing, and 10 is not a prime number. So both of those, this is true, and this part is true, which makes the whole thing true. 13 is a perfect number, and 4 is a prime number. Well, the fact that we know 4 is not a prime number, this is false. It doesn't even matter what this one is. It automatically makes the whole statement false. So when we do a conjunction, if we know even one part's false, we automatically break it. This is heads up for later on, where we're trying to show that a conjunction is true. You have to show both are true. Or all you have to do is break one of them. But the rest of you, that makes it kind of nice and easy. All right. On the other hand, a disjunction is an or, and it's false if both are false. It's the opposite situation. It's only false if both are false. If at least one of them is true or both are true, then it is okay. So again, let's come back. The bass is located on the campus, or 5 plus 2 equals 8. Well, we know that this first statement about the bass, that is true. And this part is false. So that actually makes the whole statement true. If we go to our next one, it is snowing today, or 10 is prime. Well, here's the interesting part. Both those are true. So that would actually make this, again, true. If we go and so I'm just using this as an example. Again, we can go here. This one, again, it now is important to know, is 13 a perfect square? It is not a perfect square. If you know your perfect squares, that would be 4 and so forth. In fact, this is backwards because 4 is a perfect square and 13 is a prime number. So this statement's actually false because both of these statements are false. So that's the idea behind how we use conjunctions and disjunctions. Now, we can also use truth tables to kind of understand these. Now, because there's 4 values of P and Q, because if P is true, then Q can be true or false. So notice this right here gives us the 4 options that we can have: true and true, true and false, false and true, and false and false. So the question is, which of these are true and which of these are false? So remember, what does this symbol right here represent? Hopefully you're thinking this is an and symbol. This is the conjunction. So they both must be true. So in that situation, select my thing, come back over here. Sorry about that. This is true. But if one of them is false, it turns out this is false all the way. On the other hand, this symbol is the or symbol. So again, this is the and symbol. This is the disjunction, which means that at least one of them is true. Well, that makes this true. That makes this true. That makes this true. And that makes this one false. Now, I want to point something out. This is kind of important that people get misled. In normal English talk, if I say that you can take this class or this class, we are excluding and saying you could take only one. You can't have both. That is not logic. In logic, or allows both situations to be true and has many, many more. So we have to be aware of that and utilize that in our time. All right, so that's what truth tables, and again, here's it typed out pretty. Let's talk about exclusive or, because that is a situation where exactly one of them is true. It's false otherwise. So if they're both true or they're both false, you actually lose it. That actually, in this situation, we use this funky symbol, looks like a plus symbol inside of a circle. And it means exclusive or. Now, we don't use this a lot because the truth is you can create exclusive or using conjunction, disjunction, and negation, a combination of those. So in reality, most of mathematical logic is not based at all on exclusive or. It's based on conjunction, disjunction, exclusive, negation, conjunction, and disjunction, not and an or. All right, so we got this. Now, and this is what I mean. I can literally write this though as P or Q and not P and Q. So this situation right here, notice if both of them are true down here, this is true, the negation makes this false. So an and, it kills it out. So this portion right here only has a problem if both are true. And this is the normal. And so that's why it works out to be beautiful otherwise. All right. I'm going to toss another symbol, and this is triple equal sign. In logic, we do not use the equal sign. It's not a real, it means something for numbers, but it doesn't mean anything for logic. So we use this to denote if two statements are actually logically equivalent. That means they are both true at the exact same values. So in other words, is P equivalent to not P, a double negation? Well, let's look at P. It's true and false. Not P is false true, but not P would make this true and false. And notice real quickly that these two columns are identical. That means that they are logically equivalent. At this stage of your mathematical experience, that's probably the best way to show logical equivalence of two things is to show that in a truth table that they have the exact same values. The two columns are exactly the same. So they're true at the exact same times and they're false at the exact same times. And that lets us go on. All right. So because our truth tables are identical, what about not P and Q versus not P and not Q? Well, let's build a table. So we have P, we have Q, we have not P, we have not Q, we have P and Q. Well, not P and Q is going to take this column right here and just negate everything. So the true becomes a false, false becomes true, true, true. So this is one column. Not P and not Q, I'm going to have to look at these two columns right here. It's an and statement. So it's saying, when are they both true? Well, the first two, that's going to be false. That's going to be false because I still have a false in there. That's still false. And that's true. Now, here's the question. Are these tables the same? Are these columns the same? Quick look, you'll probably recognize they're not the same. And thus, we can actually go ahead and just know that they are not logically equivalent, which is the key move. So these are not logically equivalent because their truth tables are not identical. Talk later on about what to do in this situation. In fact, it's called De Morgan's law. This is what we're going to talk about. So De Morgan's law means that not P is congruent. Here's the funny part, to not Q and not P and not Q. So notice the negation distributed and it changed the and to an or. Now this is a typo right here. This should be a not symbol. If I do negation of the or, so let me scribble that out and make that quick correction. Not P or Q is the same thing as not P and not Q. So De Morgan's law tells us specifically if I negate outside. Now, this tells us also order of operations. The parentheses, just like anything else, that's what we attack first. If that doesn't work, we then have to come back and attempt a different kind of approach. All right. So if I was to negate Jim is tall and thin, well, that would say Jim is not tall or, so the and becomes an or, not thin. So one of them just has to fail to make it not true that he's tall and thin. Now, this gets us also into something called a tautology and contradictions. It's always interesting when the truth values, everything in the column is the same thing. Like if I do this and everything is all true or everything is all false. If they're all true, we call that a tautology. If they're all false, we call it a contradiction. Your book uses a T for tautology and a C for contradiction. You can see where that comes from. That makes perfect sense. And something that's neither of those we call a contingency, meaning it depends. So let's consider this. This is an example of a tautology because P or not Q is always true. So because that is a tautology. On the other hand, if I was to say P and Q, if I had one more column, I don't have it on here. Let me add on a column. If I said P and not P. Well, that's always false, so this would be a contradiction, while this is a tautology. So that is chapter 2.1. Play with these symbols, get to know them a little bit more. We're going to use them a lot, and they're going to be your friends. Let me know what questions you got.